Hello, hello. Just testing the audio. Can everyone hear me? All right, cool. So there might be a bit of lag because it's a streaming service. So I do apologize if there is, but I'll try my best. All right, so while we're waiting for everyone else, I'm gonna basically give a brief overview of what we are planning to do. So today and tomorrow's session will be slightly different to the revision seminars that you might be used to. So instead of having slides, we're going to go through hand-picked questions from specific papers. So we're going to link all of the, so you'll be given the handouts after the session's ended, so you can use that as your revision, and the solutions will be posted as well. Cool. Okay. All right, let's get started. So let me open up. And yeah. Can you guys see the revision handout? Just while we're waiting. If you can, I will get started. Cool. No worries. Okay, so we're going to go through set theory. There's very little that they'll ask you with set theory, but the main ideas that you really need to know with regards to set theory is things like how to compute power sets. So if you're given a set, how would you compute the power set? How would you compute things like the Cartesian product and the union? So as an example, we'll go through this problem. So let A be this set containing 2019 and B is this set 1081, and we want to state the power set of the set difference. So if you recall from way back when you first touched on set theory, if we have something like A minus B, that really just means it's a set of things inside A that is not in B. Right, so for part A, recall that A minus B Well, that's all of the elements in A that is not in B. So if we have a look at this, we see that 0 and 1 are clearly elements in B. So that means in our set difference, 0 is not in our set and 1 is also not in our set. So what's remaining is just 2 and 9. Right? And so once we have that, we can start computing the power set. So the power set, remember, this is just the set containing all of the subsets of A minus B, right? So one such subset is the null set. So the power set of A minus B, let me just erase this and I'll start again. A minus B. Well, one of the subsets of A minus B is the null set. Another set is just a set containing 2, right? So we just take elements one at a time. And again, with 9 as well. Part of the difficulty with today is trying to write with my mouse. And the last set that we have is just the whole set itself. So remember that the whole set is also a subset. And so we have 2, 9. And then we close it off because it is a set. Yeah. So the power set of A minus B should contain 4 elements. Remember that the cardinality of a power set is 2 to the power of the number of elements in your set. So that's how you can tell that you have also got everything that you need. Cool. I will just erase this for now. For part B, what we want to compute is the cardinality of the Cartesian product. So remember that the Cartesian product, what you'll get in the end is basically a set of ordered pairs, right? So you want to take an element from A. So remember that A cross B is going to be the set such that you have A, B. So you have an ordered pair where A is in A is an element in A, and B is an element in B. Right? So that's something that you kind of need to remember. So it's an ordered pair, so that means the order does matter. And so how many elements do we have in the Cartesian product? Well, if you pick an element A, you'll need to get every single element B. So what that really means is that for every element A, you pick one element from B. And remember that for a set, duplicates don't matter, right? So this is just the same as 1, 0, 8, right? So we can treat B the same thing as 1, 0, 8. And from here, it's pretty obvious that for every element A, we need to pick one of 3 elements in B. And so because you have 4 elements in A, then you'll have 3 elements in B. So your final answer should be just the product of the 2. Right? Because for every element A, you want to pick one of 3 elements in B. and then you do it 4 times. You do it for 2, 0, 1, and 9. So what you get here is just the product of the Cartesian, or of the sets. And so the cardinality of A is 4, and the cardinality of B is 3, and you get 12 in the end. So there are 12 elements in A cross B. Cool. Everyone so good so far? All right, for part C, you want to calculate the cardinality of the power set of A union B. Doesn't this mean we are double counting 1, 1? No. And the reason for this is because the only way we could double count 1, 1 is if we included the 1 in this set, right? But we can see that we are discarding this 1 because our set B will only be this set here. Because remember that for sets, duplicates don't actually matter. And so what that really means is that we take 4 elements here and we take 3 elements here. And for every element A, we have an element in B. And that's how you can tell that you're not double counting any ones. Because the only way, so there is a 1 in both sets, but that doesn't really affect anything, because remember that A cross B has a specific order. So because A cross B has a specific order, then you only really count 1, 1 twice. 1, 1 once, sorry. Yeah, so A cross B is not the same as B cross A, because the order in which you do it, it does matter. Wouldn't the set 0, 1 and 1, 0 be considered the same? So, remember, okay, so I think there's a little bit of a misunderstanding with the whole notion of a Cartesian product. It is a set, but they're ordered pairs, right? So they aren't sets. So for every single element in your Cartesian product will be A, comma B with your round brackets. So 0, 1 is not the same as 1, 0 in the sense that we have ordered pairs. Cool. Does anyone else have any questions? It's really good that you guys are asking questions because it means that you're thinking. And sometimes I also make mistakes, so please let me know if I do make any mistakes. All right. So for part C, we want to calculate the cardinality of the power set of A union B. So the easiest way to do this is to just calculate what A union B is. So remember that A union B is just, the union of A and B, right? So we take all of the elements A, and then we only add elements that we haven't seen in A. So if we take all of the elements in A, that gives us 2, the hardest part of live streaming is just writing it up because I don't have a tablet. 2, 0, 1, 9. And then we look at B and we see we've already got the 1 here. We've already got a 0. We don't have an 8. So we just add the 8 on. Right? So A union B is just 2, 0, 1, 9, 8. And so what that means is that the power set, the cardinality of the power set of A union B. Remember that this is just 2 to the power of the number of elements in A union B. B. And we can see that there are 5 elements in A union B. So what that means is that we have 2 to the power of 5, which is 32. Cool. Does anyone have any questions with this? I'm going to invest in a tablet, hopefully, so my writing doesn't become a mess. Okay, if no one else has any questions, that is pretty much it for this question. Yeah. Okay, so another typical question that you'll be given in set theory is using the laws of set algebra and then simplifying an expression. And you always want to check to make sure that what you actually ended up with does indeed make sense. So let's think about this in terms of a Venn diagram, and let's see if our final answer does make sense with it. I'll pick red. So what does this look like? Well, let's just have a look at this. If I have 2 sets, A and B, well, I want to find the set difference between A complement and A and B complement. So if we have A and B complement, well, it's the elements that are in A and not in B. So that means you have these elements here. Right? And so what that means is your set difference is going to look like this. Pretty much everywhere else. Including here. Oh, jokes, it's not there. Oops. I will redraw this. Oh my gosh, okay, that's not working. Should be something like that. Cool. So basically, what you should end up with is something like, so we think that it should be equal to A complement, because pretty much this is always going to be contained in A. So if you're taking away elements in A, then that means you're not really taking anything away from this set here. So that means we think that it should be A complement. So let's prove that this is true. So I'll use black. So how do we do this? Well, if we recall the definition of A complement, or the set difference, then we know that the set difference is all of the elements in the first set that's not in the second set. So the first step is to just simplify this in terms of the definition of what a set difference is. So all of the elements in A complement, but is not in A and B complement. All right, and we can just say the definition. The definition of set difference. I'm just gonna write minus. Hopefully you know what that means. Cool. Okay, so from here, well, we have a complement and a complement, so we can use the other version of De Morgan's law to kind of simplify this a little bit. So this will become A union. So the intersection and the union should flip. and then you take the complement to the outside. You basically factorize the complement out. And that is just by De Morgan's law. Yep. Now we have A union A and B complement. So if you look at this, if you look at this portion here, what you'll notice is that A has to be involved here, and A is also involved in this portion here. So one of the really nice, and I guess one of the most uncommon properties, is that we can actually simplify this to A. And this is by the absorption law. So if we have, so the textbook calls that first step difference law. I mean, yeah, as long as the marker knows sort of what that means, we can use definition of set difference or the difference law. But it's the same idea, I guess. So for this step here, we simplify this to A, and that's just by the absorption law. So this becomes A complement, and this is just absorption. So you can use absorption law if you have a set, union, a set, and another set here, or the intersection here and then the union here. So that is just the absorption law. And we can see that what we have at the end is what we wanted, which is A complement. So we have proven that A complement minus A and B complement is just A complement. Does anyone have any questions, or is it all good? Yeah. So this is a very common question that you might see in your exam, especially if it's online as well. Basically, just know the basic laws, and then just simplify it however you can, and then you get to your answer. And you should always check your answer to make sure that it does make sense. Yeah. Cool. All right. So this is a very uncommon question. I don't see this question pop up a lot, but it has popped up in the past. Yep, I can explain absorption law. So one of the properties, or one of the laws that we have, is the following. So if we take a set A, and then we take the intersection of the set itself and something else, B, then we can actually use what we call distributive law, and we can just expand that out to A union A. Well, I guess if we expand it out, we get the same thing here, I guess. A intersect B. This becomes A union A and B. So now what we get here is another version of the absorption law. And yeah, so basically what this is saying is you take either the entire set A, oh, that is not what I wanted. You either take this entire set A, or you take this middle part here, and you'll be able to see that it does actually end up being A. Yeah. So yeah. By checking, do you mean using a Venn diagram? So it's something that you should use to check to see whether it makes sense. But you should never use a Venn diagram as your proof, because proof by picture is something that is looked down upon, because there are a lot of issues when it comes to using a picture as the basis for your proof, but you should always use a picture or a Venn diagram to check that the solution that you get in the end does make sense. or that you haven't done something wrong that gives you such a weird answer. Yeah. Cool. I will continue. So for this question, we want to find a bunch of intersections, and we want to find infinitely many of these intersections, and we want to find what this ends up being. So in order to do these problems, the first thing I would always do is just to think about like, okay, what are the first few sets? So if we take I equals to 1, if we plug it into here, well, this part here becomes 1. This portion here becomes 1 plus 1 over 1, which is 2. Then you take the intersection of the next portion. So 1 divided by 2, and well, 1 plus a half, which is 3 over 2. Intersect, and then you repeat it. 1 over 3, and 1 plus 1 over 3. And you keep going in this manner. So now if you take I to approach infinity, so when I approaches infinity, well, this portion here will go to 0, because 1 divided by a really large number will go to 0. And because this goes to 0, this portion here will go to 1. So basically what that means is that your last set should be 0, 1. And so what you actually end up doing is you're taking a bunch of these intersections, and the very last term would be 0, 1. Is this sequence? This is not sequence. This is technically part of set algebra, but I can see that it sort of resembles a sequence. So I don't think this question will be asked in your final exam, but it's always worth going over, just to ensure that, you know, I cover the scope. Okay, so when you take I to go to infinity, you'll end up with 0, 1. So the idea is that now you want to take the most restrictive region. So you want to take all of the elements that is visible in this interval, and in this interval, and this interval, and this interval here. And you'll be able to see that there's only one element that is clearly visible in all of these intervals, and that is equal to just the set 1. And so if you take these infinitely many intersections, the only element that you get in the end is 1. And so that means the answer to this is just 1. Does anyone have any questions? Cool. All right. That is pretty much the end of set theory. There's not a lot involved in set theory because it's a fairly short topic. But the bulk of the first half is really on modular arithmetic, which is probably one of the harder parts. Why is it a set? So it is technically a range, or it is technically an interval. It's just 1, 1. But 1, 1 only contains one element. So that's why we put it as a set. But writing it as 1, 1 is the same as writing it as a set. Cool. So we move on to modular arithmetic. So this is not a very common question that you'll be asked, because I know that proofs aren't a big thing in your final exam. but I will do it in case anyways. So suppose that the greatest common divisor between A and M is equal to D. If X is a solution to this congruence relation, then so is X plus M over D. So the first thing I look at whenever I do this question is, all we know is a relation, or we know some sort of information about X, namely that X is the solution to this congruence relation. Doesn't it only asymptotically approach 1? We're allowed to say it's 1 on the right side of the intersections. Well, you are correct in the sense that it does asymptotically approach 1, but we also know that 1, or the element 1, is involved in every single one of these sets, right? Or every single one of these intervals. And so it's still valid to say that the right-hand side is equal to 1, because if we take a large enough interval, then you'll have no elements that is in any one of these sets. And so that's why whenever we take the intersection of infinitely many intersections, then we really consider what happens to the very last set, or the very last interval. Yeah, cool. All right. So for this question, what we have here is all we know is that X is a solution to this congruence equation. So this is another way of saying that AX minus B is congruent to 0 mod M. And so what that means is that we can write AX minus B as a multiple of M. So this really just means that AX minus B is equal to M times N, where N is an integer. Right. All right, so that's going to come important to us. Ooh, that should be closed. Okay, let me just write this a little bit clearer. So that would be that. Okay, so what that means is we have this relation now. We're going to keep that in the back of our minds. We're going to use it later on. Okay, so we want to see what happens when we plug in X plus M over D. And we want to see that this actually ends up being congruent to 0 mod M. So if we plug this part here in place of X, what we actually end up with is A times X plus M divided by D minus B. Well, if we expand that, then we get AX plus A times M divided by D minus B. Well, if we just rewrite it like this, then what we have here is the following. And we want to show that this is a multiple of M. Because this portion here, we've already defined that as, I'll write it in. Remember that this portion here is M times N. So this part here is already a multiple of M. And we want to show that this is a multiple of M. Well, that's pretty easy, because we know that the greatest common divisor between A and M is D. And so All right, because GCD of A and M equals to D, that means that we have that D must, so that means D must divide A for this to even make sense. So for the GCD to make sense, that means D must be a divisor of A. And so what that means is that we can write A as a multiple of D. And so from here, we just plug this back into our equation here. And so what that means is x plus m divided by d minus b equals to, well, this is going to be m times n. And over here, the d's will cancel. And so what we are left with is just k times m. And we can see that this is, I'll probably state that k is also an integer. Yeah. So that means m plus k times m, but that is also congruent to 0 mod m. Right? So what we've actually proven is we assumed that x was a solution to this congruence. And so we can write it as ax minus b is congruent to 0 mod m. And so from here, we know that what this means is that ax minus b must be a multiple of m, where n is an integer. And so what we did was we considered x plus m divided by d. And notice that this can be written as ax minus b plus this part here. And we already know that this is a multiple of m. So we wanted to show that this was a multiple of m as well. But that was pretty easy because we know D must divide A for the GCD to make sense. And so we end up getting this result here. So that means A times x plus m divided by d minus b is congruent to 0 mod m. And so therefore, A times x plus m divided by d must be congruent to b mod m. And we have the result that we wanted to show. So it's just about taking steps and ensuring that you don't skip any steps, and then you get to the result that you need. Cool. Does anyone have any questions with this? All right. Now we get to the interesting questions. So we know that m is the product of all primes between 10 and 20. N is a product of all numbers between 20 and 30 inclusive. And we want to find the GCD of m and n. Okay, so whenever you see GCD, the first thing you should always think of is, oh, I need to prime factorize both of these numbers, m and n. Because if you try to compute m and n directly, you'll find that they're fairly large numbers. And then finding the greatest common divisor between two really big numbers is pretty difficult to do, at least by hand. So we need to find another mechanism to be able to calculate the GCD a lot easier, a lot quicker. And so the next best thing to do is to just compute the prime factorization of the greatest of m and n. Okay, so that's what we're going to do. So for part A, we want to just find the prime factorization of m. That's pretty easy because m is just a product of primes. So if you think about all of the primes in M, Well, that's just 11, 13, well, 15 is composite, so 17 and 19. 19. What about n? Well, let's just do it one by one. So the prime factorization for 20, well, 20 can be decomposed down to 2 times 10, but 10 can be decomposed down to 5 times 2. So 2 squared times 5. That will give you 20. All right. What about 21? Well, 21 is just 3 times 7. And 3 and 7 are prime numbers, so we're all good. What about 22? Well, 22 is just 2 times 11. And what you'll observe is that 11 pops in both of these numbers. So I'm going to highlight that. Let's do it in. So we have this 11 here. So we're just going to highlight these. All right, let's keep going. So this was 22. What about 23? Well, 23 is prime. So that's just 23. 24. Well, 24 is, let's see, 2 times 12. But 12 can be decomposed down to 4 times 3. And that will become 2 cubed. Right? So 2 cubed is 8 times 3 is 24. All right. What about 25? Well, 25 is just 5 squared. (26) is 2 times 13. Again, you see that a common number pops in both of them. So we'll highlight that. So we have a 13 here and we have a 13 here. So let's keep going. So the next number is 27, but that's just 3 cubed. So we'll write it like that. And that's just 27. 28 is 4 times 7. 4 is 2 squared. So we get 2 squared times 7. And then we'll continue. Multiplied by 29. But 29 is prime. So that's just 29. And 30 is 3 times 10, but that is just 2 times 3 times 5. All right, so we finished the prime factorization for n, so this really long number. And we can see that the only numbers that are common in both m and n are 11 and 13. So that means the GCD of m and n must be 11 times 13. And we're done. Can we just say 13 is the GCD because, well, 13 isn't the GCD of m and n, right? Because 22 can be decomposed as 11, or 2 times 11. So in order to be very careful, it's better to just do the prime factorization, because then you'll be able to see maybe certain elements that you might have missed, or you might have, but yeah, basically the whole idea is to just decompose it down into its prime factors, because we know that m and n have unique prime factorization. So yeah, the GCD of m and n is just 11 times 13, and you can check that that is correct using a GCD calculator. Yeah. So there are probably other ways of doing it, but this will be very helpful for the second part. So that's just something to keep in mind, because you always want to do things to simplify your working for any previous any parts that you haven't done. Because for part B, all we need to do is, well, once we've decomposed n down to its prime factors, then what we know here is, well, 10 can be decomposed down to just 5 times 2. And so it suffices to just find all of the pairs of 5 and 2. So there is no other way to decompose 10. So we just need to look at 5 and 2, the pairing for 5 and 2. So we can see that we have 2, 3, 6, 7, 8, 9, 10. So we have 2 to the power of 10 times 5, 3, 4. So we have 4 5s. So the maximum we can take is 2 times 5 to the power of 4, because that is the minimum power that occurs in both of them. And then we just multiply it by whatever is remaining. But notice that we can only have up to a power of 4 of 10. So the highest power would be just 4. Does that make sense? And that really comes down to basically decomposing it down to its prime factors. And then from there, you think about how you could pair 10, which the only way to do that is just 5 times 2. And then finding all of the 5 times 2 pairings in your number n. And that will give you the answer here. Cool. All right, so this one is a very common question that you guys have done probably so many times before. But for those of you who are still unsure of how to do it, I will kind of just speed through it. So there are 2 cases that you kind of want to consider. So the first case is to figure out whether they have solutions, because there's no point in trying to find solutions to something that clearly doesn't have any solutions. So you'll be able to tell if a congruence equation has solutions if and only if the greatest common divisor between say A and M. Okay, so if we have this congruence relation, let's do it like this. So suppose that we have a congruence relation AX is congruent to B mod M. This will only have solutions if the greatest common divisor of A and M divides divides B. So if it doesn't divide B, so your first scenario is if the greatest common divisor between A and M does not divide B, we say that this has no solutions. So if the greatest common divisor between A and M does not divide B, no solutions. Otherwise, if the greatest common divisor between A and M does divide B, then we have GCD between A and M, many solutions. Many solutions. So for example, if the greatest common divisor was 1, then you have 1 solution. If it's 2, then you have 2 solutions, and so on. Okay, so these 2 are the main cases that you kind of have to just think about in order to figure out if your congruence relation or congruence does have any solutions. Okay, so for part A, 15x is congruent to 7 mod 21. Well, the greatest common divisor between A and M, well, A in this case is 15, M in this case is 21. So A and M must be equal to 3, right? And we know that 3 does not divide 7, so therefore we have no solutions. Oh, no solutions. Cool. So for part B, we know that clearly 3 does divide a 9, so we will have 3 solutions. Now, to find your solutions, the first thing I always like to do is to just break it down into the simplest case. So here we can clearly see that 3 divides every single number here. So let's just divide everything by 3. And keep in mind that we do have 3 solutions. So I'll write it here. We have 3 solutions. So we need to find the 3 solutions. So if we divide every term by 3, we end up with the congruence 5x is congruent to 3 mod 7. And so what we want to do is to just write this as 5x minus 7y, or plus 7y, it doesn't matter. That should equal to 3. And we want to find the coefficient that is associated with the 5. All right. So now what we're going to do is we are just going to calculate the greatest common divisor between 7 and 5. And to do this, we just have to use the Euclidean algorithm. So we take 7, well, 7 is equal to 5 times 1 plus 2. So 5 becomes 2 times 2 plus 1. And you'll be able to see that we end up with 1. And so the next term here, you'll have a 0 as a remainder. And so we stop here. So the next step is to just apply the reverse. So to do this, we solve for the remainder. So 1 is equal to 5 minus 2 times 2. And then you replace the 2. You replace your 2 with 7 minus 5 times 1. So 5 minus 2. So instead of writing it as 2, we write it as 7 minus 5 times 1. Right? And so from here, we can just simplify it. We get 3 times 5 minus 2 times 7. And you'll be able to check that this is actually true. So 1 is equal to 3 times 5 minus 2 times 7. So this is almost in the form that we want. The form that we wanted had, well, the single term being equal to 3. So we can just multiply both sides by 3, and we get our solution for x. So here, 3 is equal to, well, it's going to be 6 times 5 minus, well, 3 times 2 gives us 6 times 7. Oh, that should be a, yeah, that should be a 9, not a 6. Let me just erase this. That should be a 9. Cool, and 9 times 5 is 45, minus 42 is 3. Awesome. Okay, so you know that one of our solutions must be equal to 9. To find your remaining 2 solutions, we just add, or 7, right? So plus 7, which is 16. And remember that we're working in mod 21. So that's just something to keep in mind. So the next term would be 16 plus 7, which is 23. So 23 is clearly bigger than 21. So we reduce it down to And so our final solution is 2, 9, and 16. Yeah, does anyone have any questions? It's a fairly lengthy process, but it's the same process every time. So once you learn the technique, then it's basically 3 marks. So just to recap, you have no solutions if the greatest common divisor does not divide B. You have GCD-AM many solutions if it does. You just apply the Euclidean algorithm and you apply it in reverse to get your solutions. Cool. All right. Okay, so this next question is a very common question that you see a lot in past papers. And it's basically using the fact that we want to find this result in order to find this huge sum. So the first part is fairly straightforward. You just basically keep increasing n until you hit 1 mod 57. So 7 to the power of 1, well, clearly that's 7 mod 57. If you take 7 squared, well, you just multiply this result by 7 and you get 49 mod 57. And when you do it again, you'll end up with 1 mod 57. Cool. So your answer here would be 3. All right. We're going to use the fact that 3 gets us back to 1 in order to rewrite this expression here. So the reason why this is so useful is because when we take 7 to the power of 4, that reduces down to 7 to the power of 1. And 7 to the power of 5 reduces down to 7 to the power of 2, and so on. So what we can do here is when we take the sum, so if we take the sum of 7 to the n up to 1,000, what we get here is, well, that's 7 to the power of 0 plus 7 plus 7 squared plus 7 to the power of 3. But then when you add any extra terms here, well, 7 to the power of 4 is just 7 to the power of 1. So we get 7 to the power of 1 again. 7 to the power of 5 is just 7 squared. So we have 7 squared again, plus 7 cubed, and so on. So now we just need to figure out how many of these terms we have. So we have up to 1,000 terms. So if we just discard the 7 to the power of 0, then we have 1,000 of these terms. So in order to figure out what the very last term reduces down to, we take 1,000 divided by 3, because the cycle is a cycle of 3s. And so what that gives you is 3 times, well, okay, what I'm going to do is, well, 1,000, yeah, so 1,000 can be written as 3 times 333 plus 1. And so what that means is 7 to the power of 1,000, that reduces down to 7 to the power of 1. And the reason for this is because we can write 1,000 as this, but then 7 to the power of 3 so there must be one leftover power. So this residue tells us how many powers are remaining. And so because there is only one leftover power, it must be the start of a new series here. And so what that means is 7 to the power of 1000 reduces down to 7 to the power of 1, which is just 7. So this entire sum here, well, that reduces down to 7 to the power of 0 plus 3 times 333. What am I doing? It's 333. Yeah, so 333 times 7 plus 49 plus 1. Because remember that 7 to the power of 3 is equal to 1, which we found here. And so what that means is you have this extra 7 left over. So when we reduce it in mod 57, this entire thing goes to 0 because this is a multiple of 57. And 7 plus 49 plus 1 is 57. And so what that means is you're left with 7 to the power of 0 plus 7, which is 8. And so your final solution should be 8. Does that make sense? Does anyone have any questions? So the trick is to use the fact that 7 to the power of 3 is congruent to 1 mod 57. And from there, you just divide 1000 by how many of these terms that you have. Well, you have 333 threes plus 1. So that means 7 to the power of 1000 reduces down to 7. And so when you take the sum and then you reduce it in mod 57, you end up with the first term plus the last term, because the middle term goes to 0. And so you get 8. Cool. Okay. We're running out of time a little bit, but I will just do my best to do these questions. So there's only a few more questions. Yeah. But those were the sort of the main problems with regards to modular arithmetic. Now we're going into things like relations. So we're going to discuss relations, namely equivalence relations and partial orders. And then we're going to go through some function problems. So if S is R squared, which is the set of all ordered pairs of real numbers, and we want to define a relation such that they are related if and only if there exists a positive number lambda such that x2 equals to lambda x1 and y2 equals to lambda x1 or y1. And want to prove that it's an equivalence relation. So you want to prove three things. You want to prove that it's reflexive, which is pretty obvious. If you just set, so it is related to itself, x1, x2, well, that's related to itself because we can set lambda equal to 1, right? And if we set lambda equals to 1, then we have x2 equals to x1 and y2 equals to y1. Cool. The next thing you want to prove is symmetry. It's symmetric. And to prove that it is symmetric, what we want to show is we want to show that if A is related to B, so if we take A1 and A2 and we assume that it is related to B, so B1 and B2, And then we want to show that this also means that B1, comma B2 is related to A1, A2. And to do this, because we assume that A1, A2 is related to B1, B2, that means that we have B1 equals to lambda A1 and B2 is equal to lambda A2, right? And so from here, what we can do is we can write A1 as 1 over lambda times B1. And we know that lambda can't be 0 because, well, if it's equal to 0, then we set B1 and B2 equal to 0. Otherwise, we assume that it's not 0, and so we can divide by lambda. And in the same way, A2 is equal to 1 divided by lambda B2. And what this means is that B1, B2 must be related to A1, A2. Because remember that we only require lambda to be a positive number. So if lambda is positive, then 1 over lambda must also be positive. And so doing this will allow us to prove that it is symmetric. The last thing you want to show is transitivity, which isn't too hard to show. I think it's fairly obvious. But basically, the idea is that if you take A1, A2 is related to B1, B2, and then say B1, B2 is related to C1, C2, then we want to show that A1, A2 is related to C1, C2. And to do this, well, we have two equations. So if we take B1, so we have B1 equals to lambda A1 and B2 equals to lambda A2, and we also have C1 equals to lambda B1 and C2 equals to lambda, or maybe not lambda, sure, this is mu B2. From here, we can just substitute this expression into here, and we can substitute this expression into here, and we do end up with C1 equals to lambda mu A1 and C2 equals to lambda mu A2. So from these two expressions, we conclude that because lambda and mu must be positive, the product must also be positive. And so that means that A1, A2 must be related to C1, C2. And so we have proven transitivity. So fairly straightforward, I think. This is a very easy mark to get in your exam. As long as you remember that for an equivalence relation, you need to show reflexive, symmetric, and transitivity. Cool. And the second part is to just geometrically describe the equivalence classes. So remember that it's two ordered pairs are related if there is a positive number lambda such that this holds. Well, that really just means that two things are related if they are multiples of each other. So x1, x2. So that's the same thing as saying if you take two vectors, y1, y2 here, that's equal to lambda, meaning that they are multiples of each other. So that will describe all of the equivalence classes for this relation. Oh, man. Okay. All of the equivalence classes for this. So they are multiples of each other. Of each other. Yeah. Cool. All right. So that's how you do these types of problems. All right. Cool. All right, so now we have a relation that is not necessarily an equivalence relation, but it is a what we call a partially ordered set. And what this means is that there is some ordering that is attached to it. And then we want to draw the hash diagram. So to do this, we basically just want to, if they ask for a geometric description, shouldn't we say it's like the set of straight lines through the origin? Yeah. So that is definitely a really good description for the question. It does say geometrically, so you should have some sort of geometric interpretation of what they mean. So saying it's a straight line through the origin is perfectly fine as well. Yeah. Cool. All right. So, and I think that is actually preferred in this case as well. So if we want a partially ordered set, then we need to prove three things very similar to the equivalence relation. But instead of proving symmetry, we want to show it's anti-symmetric. So I will leave the first one and the last one to you guys. Basically just proving that it's reflexive and it's transitive. That should be fairly straightforward. But to show that it's anti-symmetric, we assume that A divides, well, in this case, the relation is divides. So we assume that A divides B and B divides A. And we come to the conclusion that A should equal to B. Right, so we want to show that A should equal to B. Well, if we know that A divides B, then there exists a number, or there exists an integer m such that B equals to m times A. And in the same way, if B divides A, then there is an integer n such that A equals to n times B, right? So from here, what we want to do is plug one of the equations into the other. So B equals to m times, well, A can be written as n times B. So we can just replace A with n times B, and we can simplify it like this. M times B. So what that means is m times n should equal to 1. But because we know m and n are integers, that means the only solution to this equation has to be when m equals to n equals to 1. And so from here, what we can conclude is that this means that a equals to b, and this also means that b equals to a, or the other way around. And so what we can conclude is that a must be b. So we assume that a divides b and b divides a, and then we arrive at the conclusion that a equals to b. And that is how you can show anti-symmetric. So you'll still need to prove the other two properties, that it's reflexive, which is fairly straightforward, and that it's transitive, which again isn't too difficult to show. Cool. So for part 2, we want to draw the hash diagram of S. So when it comes to drawing the hash diagram, there are some things that you kind of have to remember. The first thing is that we always assume that every element is reflexive, so we don't draw any cycles, or we don't draw any self-cycles, meaning that we don't draw something like this. So this is definitely something that we don't do. And if we know that x goes to y and y goes to z, we don't draw a line from x to z. So we don't do that as well, because reflexivity and transitivity are assumed. With that in mind, let's just think about all of the all of the factors of 20, because here S is the set of all factors of 20. So that's 1, 2, 4, 5, 10, and 20. And so from here we begin our hash diagram. So 1, well, that divides 2, and that also divides 4, but 2 divides 4, so we just draw 4. 5, well, none of them divide 5, so we just draw 1 here. 10, well, we know that 5 divides 10, and 2 also divides 10, and then finally 20. So all of them will divide 20. So here we don't draw a line from 2 to 20, because we can travel from 2 to 10 to 20, or 2 to 4 to 20. And so from here, that is our hash diagram. So as long as you know that we don't need to draw any self-cycles, or we don't draw any transitive lines, then we are okay. Cool. All right. And the very last two questions are just function questions. So the first one is to show that if G is 1-to-1 and the composition is onto, then F is onto. So here we're just going to recall what 1-to-1 means and onto. So 1-to-1 means that if F of x1, in this case it's G, so if G of x1 equals to G of x2, well, that means that x1 equals to x2. And if F is onto, then we say that for all elements y in the range, I don't know, let's just say, or the range of F is B, or in the codomain. So for all elements in the codomain of F, there exists an element x in A, such that y equals to f of x. So the range is the same as your codomain. That's essentially what it's saying. So this is 1-to-1, and this is onto. All right, so with that in mind, let's begin the proof. So the first thing is we want to look at G of f. So I'm just going to write let A be an element in A, B be an element of B, and C be an element of C. So from here, we know that f or G of f is clearly a function. So G of f, well, the domain is the domain of f, so it's all elements from the set A to the codomain of G, which is C. So it's a mapping from A to C. Okay, so from here, we know that because G of f is onto, then for all elements in C, so for all elements in C, there exists an element A, in A such that G of f of A equals to C, right? That's just by our definition of onto. All right, so now because we know that this is true, then we also know that because G is a mapping from B to C, well, C can be written as G of B. So this is the same thing as saying G of f of A must be equal to G of B, for B is an element in little b. Okay, so from here, because we know that G is 1 to 1, that means this element here must be the same as this element here. And so what that means is that f of A must be equal to B for every B in B. But then what we know here is that this is just the same as this. And so what that means is that f must be onto. F is onto. And we have the proof. Yeah. So it's just knowing your definitions of 1 to 1 and onto. And once you know the definitions, then you just apply them one by one in our expressions here. And from there, we get to the result that we want here, that f is onto. Cool. And the last question is, if x and y are sets, how many injective functions are there from x to y? So remember that injective functions really just means 1 to 1. And we looked at the definition of 1 to 1 previously here. So that means if you have a mapping from x to y, with x having 2 elements and y having n elements, then, well, for the first one, for the first element, f of x can take n elements. So it can be any one of the n elements. But because because we know that it is an injective function, then f of x2 cannot be the same element as f of x1, right? Because x1 and x2 must be different. So here we will have n minus 1 elements. And so in total, there will be n times n minus 1 elements. Or there will be n times n minus 1 many injective functions. And that concludes the first half of the So stick around for about 10 minutes and the second presenter will be presenting graph theory. But otherwise, best of luck with your exams. There will be a live stream tomorrow as well where we'll go through proofs and perms and cons. Cool.
Hi guys, so hopefully you guys can hear me, and we're gonna start in maybe around 2 to 3 minutes just to give you guys a breather, and hopefully you can finish on time. Okay, so I think we will get started now, just so we don't go too much over time. And okay, so welcome guys to graph theory, which is, I believe, the last topic you guys cover in Discrete. So we'll just get started straight away into the questions. Okay, so the first question we'll be covering is this. So find a minimal spanning tree in the following weighted graph. Show all you're working out. Okay, so for a minimal spanning tree, the algorithm that you guys would need to use is called Kruskal's algorithm, right? And I've put down the steps here below, but we'll just be using our example to show you how to do your working out. Okay, so what you would do is set up a table down below here where you list all your available edges in your given graph in the question, right? And you also list them in ascending order according to their weight. Right, because what we want to do is create a minimal spanning tree where the total minimal weight, is the least that it could be. Right, so from here, what you would do is go through all your edges in ascending order and decide whether or not you would add it onto your graph. Right, so down here I have my final minimal spanning tree graph, and you can see that I've added AB, AF, EC, but I haven't added FB. And the reason for that is because if I added edge FB onto my graph down here, then it would have created a circuit of length 3, which is what we don't want in a spanning tree. Yeah. So just keeping that in mind, you just go through your list and keep adding edges until all your vertices are connected, as you can see down here. And from there, usually the questions, they would ask you to list or work out the total minimal weight, and that's just done by adding up the weights of your edges that you've chosen. Right, so it's a pretty simple algorithm, and it's the same for all of these questions. Right. Okay. So moving on, we have this question here. So you're given a graph G, and question 1 asks if G contains an Euler path. Give reasons. Okay, so the definition of an Euler path is a path that contains every edge of G exactly once. And a good thing about Euler paths is that we have this theorem, or this concept called the existence of an Euler path, which states that an Euler path exists between two vertices if and only if those two specific vertices are of odd degree and every other vertex is of even degree. Right, so to answer these type of questions, what you would do is list out all the degrees of your vertices, and from there you can see that in this example, my vertex Q, Y, X, and V, they are all of odd degree, right? And I only wanted just exactly 2. And for that reason, this graph here does not contain an Euler path. Okay, so graph theory is pretty straightforward if you know all your definitions. So make sure you do know what an Euler path is and the existence of an Euler path and what you need to prove. Okay, question 2 says show that G is bipartite. Okay, so again, you need to know what a bipartite graph is, and this is a simple graph where your vertices are partitioned into two disjoint non-empty sets, right? And you can see here my sets, my first set would be the vertices Y, W, T, R, and P, and my second set would be my vertices X, V, S, and Q. Right, and the main thing is that no two vertices in the same set are adjacent, and that just means that there is no edge that links, say, Y and W in my first set, and so on. Okay, so how we prove this question is pretty simple, and what you can do is just redraw the graph, and what you do is essentially you move all your vertices around until you can produce a bipartite graph, and that's what we call an isomorphism of your graph. Okay, so we'll be covering this a little bit more later on, but yeah, so this is essentially how you answer this question. Okay, so moving on to question 3, this is probably the hardest part of this question, and it says to prove that G does not contain a Hamilton circuit. Okay, so moving here, the definition of a Hamilton circuit is a circuit that contains every vertex of your graph exactly once. Okay, so I have my graph down here from the question, and you can see that one simple path that you can take or circuit is if I start at vertex Y and I just go around my cycle. So I go X, W, V, T, S, R, Q, and then P, but I need to end up at my vertex Y. And you can see that the only way to do that is if I visit vertex V again, right? Because that's the only edge that I can use to get back to vertex Y. Okay, so that's one example of how a Hamilton circuit doesn't exist, but if you're not convinced, then we do have another option down here. So if we start at an arbitrary vertex, say Q, right, so we'll be starting at vertex Q in my graph, you can see that the only option I have from here is to visit vertex P. And the reason for that is because vertex P has only 2 edges incident on it. So that means I have to go through my edge QP in order to include this vertex P. Okay, so from there, you would head to P and then to V, right? And then again, same concept, I would need to visit vertex T from if I was at vertex V, because again, vertex T only has 2 edges incident on it, so I would have to use my edge VT. Okay, and then from there you would end up at vertex S, and then from here, this is where you have options. So you can choose to visit either vertex Y or R or W. Okay, so I'm just going to go with Y first, and you can see that once I get to vertex Y, yeah, the only option I have from there is to go to vertex X. And again, the reason for that is because I can't go to vertex V because I've already visited it and I just came from vertex S. So I only have vertex X as my other option. Okay, and from there you have options again. You can go to either W or R, right? So you can see that if I chose W, I would be stuck because from here there is no edge that links W to my last vertex R, right? That means that I would have to visit another vertex again if I wanted to include my very last vertex and end up at the vertex that I started at to complete my circuit. Right, so hopefully that you're more convinced that there is no Hamilton circuit, and you can see that like in your own time. If you want to try visiting vertex R first instead of Y, you can see that you'll end up at with the same conclusion. Okay, so you can see that from here it's impossible to complete the circuit without visiting any vertex again, so therefore this graph does not contain a Hamilton circuit. Okay, and the reason why we went through all this trouble to show that there is no Hamilton circuit is because there's actually no specific characterization to show that Hamilton circuits exist. Right, so remember before for an Euler path, we had this existence of an Euler path definition here. Right, so for Hamilton circuits, we don't have something like that, so we have to essentially just grind through and try and show that there is or is not a Hamilton circuit. Okay, but then we do have something called sufficient conditions, and that's another method that you could use. And this here basically states that the graph has a Hamilton circuit if the degree of each vertex is greater than n on 2, where n is the number of vertices in G. You can see that this condition is satisfied in this case. So there are 9 vertices, so the degree of each vertex is not satisfied. So this condition is not satisfied in this case, and the reason for that is because, again, we have n vertices, and n on 2 gives me the condition that each vertex has to be greater than or equal to 4.5. But we can see that a majority of the vertices are actually less than 5. So for example, vertex P and T, they are of degree 2. Right, so this condition is not satisfied, so G does not contain a Hamilton circuit. Okay, and we'll come back to this condition in a second later on, and I just want to make sure you guys keep that in mind for now. Okay, so moving on again, we have our next question, and you're given a graph here, and it says to show that the graph is not planar. Okay, so a planar graph is essentially a graph that you can draw with no intersecting edges. Okay, so I have a definition of that later on in the presentation, but we'll just be using that for now. Okay, so you guys learned a theorem called the Kurotowski's theorem, which states that a graph is planar if and only if it has no subgraph, K5, which is your complete graph with 5 vertices, K3, which is your complete bipartite graph with 3 vertices in each disjoint set, or any graph that's homeomorphic to either of these 2 graphs. Okay, and a homeomorphic graph, by definition, is obtained by just adding vertices of degree 2 onto your existing edges. Okay, I think you guys do cover that in your lectures, but just remember that definition there. Okay, so using this theorem is quite difficult. It is a lot of trial and error in deleting your edges and trying to redraw your graph to show that it has or it doesn't have a subgraph of K5 or K3. Okay, so for this question here, we first obtain a subgraph by deleting edges BC, DE, and FG. Right, so once we've deleted these edges, we can actually move our vertices around and redraw our graph to give this graph down here. Right, and this graph down here is homeomorphic to my complete bipartite graph because I have a vertex G here just attached onto my edge BE. So once you have this result here, you can just state by Kurotowski's theorem that the graph is not planar, right? Because this graph does actually contain a subgraph that is homeomorphic to K3. Okay, so I'm not gonna lie, this does take a while in deleting the edges, but I do have just a tip here. So the tip is, notice that the given graph in the question has 7 vertices, right? However, vertex G, it looks like it was just added on randomly onto edge BE and connect it to FG, right? So one tip how you could start off is just by deleting FG and then seeing where you go from there, right? Yep, so because of vertex G, that does hint at a homeomorphic subgraph, and that means the remaining 6 vertices would hint that the subgraph could be K33, because again, your complete bipartite graph has 6 vertices. Right, so it's just like little things like this to notice when you answer these questions, and it would help put you on the right track in deciding what to do from there. Okay, so hopefully you guys are okay with that. We're going to move on to the next question, which states that graphs G1 and G2 are simple and each have vertex sequence 4, 4, 4, 3, 3. Explain why G1 and G2 are isomorphic. Okay, so the best way to approach these type of questions is to just draw 2 graphs with the vertex sequence that they gave you, right? And try and make them as different as you can. So you can see in my diagram down below, I have my first graph and second graph both satisfying this vertex sequence here. Okay, so just a definition of isomorphism. So 2 graphs, G1 and G2, are isomorphic if essentially you can map the vertices of G1 to distinct vertices in G2. And you can also map the edges of G1 to distinct edges in G2. But this is only the case given that the edges incident so the edges that are incident on the vertices are preserved, right? So just make sure that incidence is preserved and you're not like mixing up which vertex is connected to which edge, right? So that is pretty important. But at the end of the day, what this theorem basically says is you want to move your vertices around in such a way that you can redraw the graph again. And if you can, then that graph is isomorphic to the first graph. Right, so if I have a look at my diagram down here, you can see that the second graph can actually be redrawn isomorphically to look like the first graph here, right? And all I did was take vertex H and shift it down to below vertex J and I, and you can see that it looks exactly the same as the first one, right? And I haven't done anything else, and that's how you know that these 2 graphs are isomorphic. Right, so isomorphic or isomorphism questions, I recommend just drawing the graph and trying to move your vertices around to see if you can prove that it is isomorphic. Okay. Okay, so hopefully you guys are okay with that because we have another isomorphic question here. So this question incorporates both modular arithmetic and graphs, which is pretty common in your past exams, so just make sure you do know how to link these two. So first question says to draw a Hasse diagram of the set of all subsets of this set S under the relation is a subset of. Right, and you guys should have covered this earlier in this presentation, so I'm just going to give you the Hasse diagram right here. Okay, so question 2 says regarding the diagram in A as a graph, so imagine this here is a graph, is it isomorphic to the 3 cube Q3? So 3 cube is just a cube, right? So you can see here that it does somewhat look like a cube, but it's just a little morphed, I guess. So what you do is you can just draw out the 3 cube Q3 and label all the vertices such that it corresponds to your Hasse diagram here. Yeah, and make sure, again, the edges are linking the right vertices. And once you've obtained this graph, you can say, yes, it is isomorphic to your 3 cube. Okay, so pretty simple as long as you know essentially what isomorphism is and what your 3 cube looks like. Okay, and then a final question asks, is the graph in A planar? Prove your answer. Okay, the easiest way to prove this, like you can use Kurotowski's, but I think going for the easiest method and the quickest method first would always be best. And the quickest method to prove a graph is planar is to try and redraw it to the best of your ability. So you can see down here that this graph is planar if I just move my vertex 1, 3 to the bottom and I just rejoin the edges as so. Right, so here you can see no edges are intersecting, so it is a planar graph. Okay, so more on planar graphs. This question here says to draw K4, which is your complete graph on 4 vertices, and then add another vertex and connect it to 3 of the vertices in K4. Is this graph planar? Prove your answer. Again, very simple. Yes, the graph is planar, and the reason for that is because you can just redraw the edges such that they aren't intersecting, right? And this is where I have the definition of a planar graph. Again, no intersecting edges, and this here is what we call a planar map or a planar representation. Okay, so you can see that A, B, C, D was my complete graph on 4 vertices, and I just added vertex E and connected it to A, B, and D. Right, and the dotted line shows what it would have been if it wasn't a planar graph, and all I've done is just move the edges around such that it is. Okay, so pretty straightforward, and I think nothing too difficult here. Okay, so one thing about graph theory is you notice that a lot of the questions are pretty similar. And the reason for that is there isn't much variety when it comes to graph theory, because the only things I can test you on are your definitions and whether you know what to look for when it says, like look for a Hamilton circuit and what the conditions are. Okay, so another question here. You're given this following graph and it says to work out if the graph is bipartite, planar, if it contains an Euler circuit or a Hamilton circuit. Okay, so very straightforward. Question 1, the graph is not bipartite, right? And the reason for that is because there are multiple odd cycles, right? So if you look at cycle A, B, and E, it's impossible to partition these 3 vertices into 2 disjoint sets, right? Because if I put A in set 1 and vertex B in set 2, then vertex E can't be in either set 1 or set 2 without having any adjacent sides. Right, so therefore you can say the graph is not bipartite, and this is actually enough to answer the question. Okay, question 2, is the graph planar? Answer again is yes, because I can just move my edge BF around such that it is not intersecting with any edges. Okay, question 3, does the graph contain an Euler circuit? Okay, so here we have a different condition or existence for an Euler circuit, and that is if every vertex in G has an even degree, then G has an Euler circuit. Okay, so again, it's very important to remember these existence conditions, and they make answering the questions a lot easier. Okay, so if you look at the graph here, all the vertices are of even degree, so you can state straight away that the graph contains an Euler circuit. And a good idea is to just list out a circuit that you can find, right? So that way you can be certain that there is an Euler circuit. Okay, question 4, does the graph contain a Hamilton circuit? Okay, here it is really simple to see that there is a Hamilton circuit because you can just go A, B, C, D, F, E using the edges in what looks like a cycle. So if you don't use the edges that are intersecting in the center. Right, so yes, there is a Hamilton circuit, and one thing I want to note is that the sufficient condition that we talked about before, it doesn't hold in this case. Right, so the sufficient condition was saying that there is a Hamilton circuit if the degree of each vertex is greater than or equal to the number of vertices divided by 2. See, in this case, the number of vertices is 6, and divide that by 2 is 3. So it's saying that each vertex has to have degree of 3 or more. Right, but you can see that vertex A and vertex D here have degree 2, yet there is still a Hamilton circuit. Right, so this sufficient condition is not satisfied, but we can still find a Hamilton circuit. So that's what you guys need to be a bit careful about for Hamilton circuits. Right, it's just a sufficient condition, it's not enough as an absolute proof. Okay, so that's why for these questions, it's always I think, important to try and find a Hamilton circuit first before using this condition. Okay. So the next question we have here is, you're given two graphs below, G1 and G2. And the question asks, are these two graphs isomorphic? Prove your answer. Okay, the answer is yes, they are isomorphic, and you can see in this table below that I've listed out which vertex is mapped to another vertex in G2 such that it is isomorphic. Right, so if you can prove that it is isomorphic, it's a good idea to just write out this table so the marker can see how it is exactly. Right, I wanted to point out something else which is called isomorphic invariance, which I think you guys went through in your lecture. So isomorphic invariants are properties that two graphs have to share if they were to be isomorphic with each other. Right, so these properties are things such as the number of edges, the number of vertices, and the sum of the degrees of all the vertices, for example. And there's like plenty more that you can take a look at. But essentially, you can always just start off with looking at isomorphic invariance just by listing out the vertex degrees of each vertex, number of edges, and seeing if these hold true. Right, so if you find one invariant that doesn't hold true, then you can say that these graphs are not isomorphic. Right, but if you do go through and you see that they are holding true, then it's always useful to just write out how each vertex maps to another vertex while preserving incidence. So this one's pretty important. Okay. Part 2 says, asks, does G2 have a Hamilton path? Again, this is a pretty simple question, and the answer is yes, because again, a Hamilton path, it just has to visit every vertex exactly once, and it doesn't have to return to the same vertex since it is a path. So you can say any path in this case, and I've just written one down here, which is I, J, K, L, N, H, M. Right? So when you look at this graph, you can sort of, I guess, infer that there will be a Hamilton circuit. And the reason for that is because usually the more edges a graph has, the more likely a Hamilton circuit exists, or Hamilton path exists. Right? And the reason for that is because the more edges you have, the more options you have to visit each vertex exactly once. Okay, so that's just an intuition that you can keep in mind, but again, it's always useful to just list out the Hamilton path that you find. Okay, question 3 asks, if the weights of all the edges in G2 are 1, then find the shortest paths from H to all the other vertices using Dijkstra's algorithm. So this is the second algorithm you guys learn, that's apart from Kreskau's algorithm. And this is the method down here, which I've written, but again, we'll just be using our example to show how to answer the question. Okay. So what I've done is set up a table down here as shown, and I just have the steps, the available edges, and in brackets the total path weights, the edge that I'm going to choose, and the distance from my given vertex they wanted you to start at to wherever I end up at. Okay? So, okay. So this is my final graph that I have. That's the shortest vertex path spanning tree for my given graph. Okay. So how we go through this table is first I start off at H. Right? So the question will always tell you which vertex to start off at, and what you do is you list out all your available edges from this vertex H to the other vertices that it can reach. Right? So I can go HM, I can go HL, HN, or HJ. Right? And in the brackets I just write the total path weights, which is just 1 in this case. Okay, so from here you can choose any of these because they're all the same path weights anyway. So I choose HM. Right, and the distance from H to M is just 1. Okay, moving on to step 2. Now that I've chosen HM, that's no longer an available edge for me, so I still have HL, HN, HJ, but because I have HM down, right, I have the option ML. So going up to my original graph, I'm just going to shrink this a little bit so you guys can see. Going up to my original graph here, I have the option of going to vertex L through the edge ML, right, because I've already visited vertex M. Right, so that here is an option that I have. But again, I wouldn't choose this option because the path weight 2 is greater than all my other available edges. And what we want to do is create the shortest spanning tree, right? The shortest path spanning tree. Okay, so I would choose HL. Okay, and you essentially just do the exact same thing for all the other steps, but keep in mind that when you choose the edge, you need to make sure that it doesn't create a circuit. Because again, you are finding a tree, and a tree can't have any circuits. Okay. So once you've done that, you end up with your tree here, and that's essentially just how you answer the question. Right, so for Dijkstra's algorithm, it's pretty straightforward. Again, for all of these questions, you just do the exact same method. Okay. Okay. So we have another question that's asking Dijkstra's algorithm for a spanning tree that gives the shortest paths from A to every vertex of the graph. Right? And this question says to just show the first 3 steps, but I just have all the steps out for you here. So we've already gone through how to do this, so make sure to just review it in your own time and make sure and see how this is actually the case. Alright, but I wanted to focus on the second question, which is asking, is the spanning tree found in part A a minimal spanning tree? Explain your answer. Okay, so a lot of students get confused by this question, and you do need to note that a minimal spanning tree is only found by using Kruskal's algorithm. Okay, so the first algorithm that we covered earlier. Okay, so Dijkstra's algorithm only gives you the shortest paths from one vertex to all the other vertices. Okay, so to answer question 2, the best way is to just do Kruskal's algorithm again. Okay, and it's a good thing that this algorithm is pretty easy and pretty fast to complete. So again, you just list all your edges in ascending order according to their weight, and you go through starting from the least weight to the most weighted edge. Right, and you choose which edges to add. Okay, provided it doesn't create a circuit. Okay, and you can see here that these 2 graphs are actually different. So when you work out the total minimal weight, just by adding up the edges, the weight of your edges in your minimal spanning tree, so the Kruskal's algorithm one, you can see that the total weight is 8, while the weight in your spanning tree in part 1, so the one that's found using Dijkstra's algorithm, is actually 9. Right, so therefore, the spanning tree found in part 1 is not a minimal spanning tree. Okay. So for these type of questions, it is possible for the graph that you find in using Dijkstra's algorithm to be the minimal spanning tree. Right, so that is possible, but it's not always the case, as you can see here. So just make sure you guys do both algorithms to double check. Okay, so those are typical questions that you would find in graph theory. They don't really stray far from these type of questions, but there is one question that might be a little bit difficult for you guys, and that's a proof question. So this question here says, to prove that the average vertex degree, which is given by this here, of a tree with n vertices is strictly less than 2. So to answer this question, we need something called the handshaking lemma. And this handshaking lemma states that the sum of all the degrees of your vertices equals to 2 times the number of edges. Okay, so this is a pretty important lemma that you guys should remember, and it's pretty useful, as you can see in this case. Okay. So referring back to the question, my graph here is a tree. Right? So for a tree with n vertices, we know that there are n minus 1 edges, and this here is a definition of a tree. that you guys will find in your lecture slides. Right, so there's always n minus 1 edges given that there are n vertices in a tree. Okay, so substituting that into your handshaking lemma, here you have sum of all the degrees equals 2 times n minus 1 in your tree. Okay, and then when you expand that, you get 2n minus 2. Okay, so know what we need here. We need to prove this summation, right, the average vertex degree. So to get this, we divide both sides by n, where n is greater than or equal to 2. Right, so doing that, I get 2 minus 2 on n on my right-hand side, and for n greater than or equal to 2, you know that this will always be strictly less than 2. Okay, so therefore the vertex average vertex degree is always strictly less than 2. Okay, so for these type of questions, again, it's very important to know your definitions. So for example, knowing that a tree with n vertices has n minus 1 edges is a crucial part in this question, and also knowing what the handshaking lemma is. Okay, and I think that is all for today. And let me just check if there are any questions. Okay, I don't believe. Let me just check. Okay, I don't believe there are any questions. Just give me a second. Yeah. Yep, so these documents will be uploaded to our MathSoc website by hopefully within the next few days. And yeah, and just to note that tomorrow we do have another live stream for the remaining 2 topics in this course. So make sure you guys sign up for that as well. And yeah, so thank you guys for listening, tuning in, and best of luck in your exams. If you have any questions, feel free to reach out to anyone in MathSoc. Yeah. Okay, bye guys.